So you've found the perfect home. But high mortgage rates have you second-guessing. The Churchill Mortgage team says waiting to buy can be a costly mistake. Try their free 15-minute analysis to see the difference between buying now versus waiting for lower rates. Visit churchillmortgage.com to learn a smarter way to build wealth through home ownership. This is a paid advertisement. NMLS ID 1591. NMLS ConsumerAccess.org. Equal Housing Lender. 1749 Mallory Lane, Suite 100, Brentwood, Tennessee 37027.
Selling your car to Carvana is as easy as...
As easy as pie?
Sure. All you have to do is enter your license plate or VIN.
As easy as a stroll in the park.
Okay, then just answer a few questions and you'll get a real offer in seconds.
As easy as singing.
Why not? Schedule a pickup or drop-off and Carvana will pay you that amount right on the spot.
As easy as playing guitar.
Actually, I find that kind of difficult. But selling your car to Carvana is as easy as...
Can be.
Visit Carvana.com or download the app to get an instant offer today.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello, once again. Thank you for joining us. This is the Space Nuts Podcast, episode 247. I am your host, Andrew Dunkley. Great to be with you again, and joining me as always is Professor Fred Watson, Astronomer-at-Large. Hello, Fred.
Hello, Andrew. How are you doing?
I'm well, thanks. How was your Easter?
Busy. With I'm right at the pointy end of the children's book, and the last bit is the cartoons, which I'm drawing.
That must be fun.
It's absolutely heaps of fun, and I really enjoy it, but they take kind of longer than you expect, so I'm really up against the deadline. But we'll see how I go. I have a bit of an extension from the publisher to the middle of this month to get the cartoons done, and I'm getting there.
Middle of this month, which is a week.
It is actually a week, that's right. Exactly. I might do some... well, I'll just have to see if I can do some fast talking. I hope nobody from New South Press is listening to this, but we're in good shape. I'm about to send off the text, which I'll hopefully do today, and probably the cartoons for the first 4 chapters, which are the ones that are actually complete.
Terrific.
Yeah.
Can't wait.
Yeah. What about your Easter, Andrew? How did you go?
Oh, my boys came up from Sydney. My eldest and my youngest live down there. My middle child, also a boy, lives just down the road from us with the 3 grandchildren, and we all got together, and it's the first time they've all seen each other in 3 years. And it's the first time that my 2 Sydney boys have met their niece, their youngest niece. So that was all very exciting, and it went well. So family barbecues, sitting around the fire pit, although it wasn't really cold enough for a fire pit, but we did the marshmallow thing, and that was a disaster. But it was it was pretty good fun. It was really nice to just sit back and do nothing and just talk about whatever we felt like talking about at the time. We usually end up having these big discussions about movies. I don't know why, but that seems to be the family topic whenever we get together. We've got to talk about something. It's better than talking about politics. Although we do that too.
Well, most people talk about what's wrong with Auntie Mabel or, something like that. So it's good that you've got something different.
Oh, we did that too. And how did you know I had an Auntie Mabel?
Oh, there you go.
Coming up in this episode, Fred, we're just going to touch on Ingenuity, the helicopter. The test is about to happen, and they're being super duper careful about this, but who can blame them? They can't send the mechanic out if the wheels fall off.
That's right.
There's also some new data that's come out of examining the Chicxulub Crater. That's that big asteroid impact that polished off the dinosaurs about 66 million years ago. Actually, it's been about a year since we talked about this, so it's 66 million and 1 years ago. There's also been a discovery of one of those elusive intermediate black holes, we think. And we're going to tackle some text questions today. We haven't done any for ages, but we're going to do a couple today, actually 2 double bungers. Yep. Andre from the Netherlands has sent us 2 questions, and so has David from Springfield. So we will get into those on this week's episode. But first, Fred, let's go back to Mars and talk about this test flight that's coming up soon for Ingenuity. The news I hear is that they have dropped the helicopter from the belly of the beast, Perseverance, and it is getting ready to be, ramped up, almost literally.
Exactly, that's right. There's a tweet from NASA's Jet Propulsion Laboratory, which I liked. This was at the weekend. I liked very much. It said, Mars helicopter touchdown confirmed. Its 293 million mile or 471 million kilometre journey aboard NASA's Perseverance ended with the final drop of 4 inches, 10 centimetres, from the rover's belly to the surface of Mars today. Next milestone, survive the night. And that's because as of, I think it was Saturday, the Ingenuity helicopter has been now relying on its own power for the heaters that keep the electronics warm, because until then it was taking power from Perseverance itself. Now it's on its own, and so it relies on the batteries, the internal batteries, and the solar panel, which sits on top of the 2 rotor blades. So hopefully that will all keep going well. The heater apparently keeps the inside at about 7 degrees Celsius or 45 degrees Fahrenheit, because the temperature on Mars drops to way, way below zero. It can be as low as minus 90 Celsius, or about 130 minus 130 Fahrenheit. So look, it's I think all is going well. As far as I know, they've checked out the solar panels and we haven't heard anything to the contrary. The first flight, now I read somewhere that it was planned for the 8th of April, but the latest is not before the 11th of April. So we still have a few more days to wait. But isn't it going to be fantastic? The first flight's going to be climbing round about 10 feet, 3 meters or so, and a hover
just
there.
Like Perseverance, which has gone 6 meters.
Yeah. It's obviously gone further now because it's had to drive over the helicopter so it doesn't accidentally back into it or something like that.
It's going to be fascinating, Fred, in that the atmosphere being so thin, it takes a lot more effort to get off the ground than it would on Earth, surprisingly. But the thing in their favour is the lesser gravity. So I'm not sure that will counter the thin atmosphere, but it will to a degree, I imagine.
Yeah, I mean, it's really going to be very interesting to see whether it works or not, given the 1% atmospheric pressure on Mars. But look, it's the engineers have done their job. My bet is that it will work just fine.
Yes. Well, everything's gone so well so far. We've just got to keep that momentum going. Yeah. And to get off the ground, they've got to achieve some massive rotational rate, haven't they? It's quite astonishing.
2,400 RPM is the rotor speed. It's pretty fast, certainly faster than your average helicopter.
If it doesn't get off the ground, we can wait till Mars is terraformed, turn it upside down, and turn it into a lawnmower.
You might have a long wait because terraforming Mars is physically impossible because the atmosphere just flies away.
Yes, indeed.
Yeah.
All right. And I notice a lot of people have been talking about this on the Space Nuts podcast group.
Good.
So there's a lot of excitement. Everyone's really looking forward to this. And look, why not? I mean, it's never been done before. This is all brand new science in terms of flying an aircraft on another planet. So we can't not be excited about this, I'm sure. But hopefully in the next week or two we'll be able to tell you what happened, because no one else will. No one else will bother. It'll just be us. Now let's move on to our next topic, and we're revisiting an old friend, the asteroid that came down in what is now the Gulf of Mexico and obliterated the planet, not just the dinosaurs. It finished them off. But there's some new research that's come out that suggested that other things happened as a consequence of this impact that probably had a big effect on why the Earth is the way it is today.
Yeah, that's right. This is something that certainly I've never thought about before, but scientists at various institutions think deeply about this kind of thing. One of the effects of the dinosaur-killing asteroid, if I can call it that. We usually call it the Cretaceous Tertiary event. In fact, it's got a slightly different name. But the KT event, when 66 million years ago, when something we think about 15 kilometres across hit the Earth at about 30 kilometres per second and caused not just a big explosion, but, all the absolute devastation that you'd expect, including a blanket of ash that would have stopped the solar radiation, probably got a kind of nuclear winter effect, all of that. And so I think, actually, come to think of it, you and I have spoken before about the effects on the fossil record in terms of the microorganisms, because we know the dinosaurs don't appear above that layer of the strata in the Earth's crust, the fossil levels, different fossil levels. So people have analysed other things, not just the traces of the dinosaurs. They've looked at fossils, for example, of leaves and pollen, and leaves tell you something really interesting, because often they've got insect bites in them. And it's apparently, this is one of the things that they've looked at. Insect bites on fossilized leaves essentially show that insect diversity fell dramatically after the event. As did plant life. In fact, the same is true with the leaves themselves. You get this decline, in fact, by an assumed roughly 45%. That's diversity of plant life. It's not the number of plants, it's the number of species of plants shot down by 45% after the impact. And the fossil record shows it took about 6 million years to recover to something like it was. But the other really interesting aspect of this work, and it comes from a scientist called Carlos Jaramillo, I think is probably how you pronounce his name, in the Smithsonian Tropical Research Institute in Panama. He says if you return to the day before the asteroid fell, the forests of South America would have been an open canopy with a lot of ferns, many conifers, and dinosaurs, of course.
Yeah. Yes.
The forest we have today is a product of that one event 66 million years ago. And essentially what they're suggesting is that the conifers and the ferns basically disappeared, and they were replaced by essentially flowering plants, but that it actually increased the canopy. The forest canopy is much greater now than it was before. Actually, another comment from one of the other scientists, Ellen Curano, she's at the University of Wyoming. I think the number one lesson here is unpredictability. When you have these major perturbations, they change the rules of the whole ecosystem. And one of the things that they're suggesting is that in the lower levels of the forest, the dinosaurs before the impact were trampling everything down and kind of eating stuff. So the lower levels were much more sparsely, variated, or what's the word for populated by plants, much more sparsely covered. So the dinosaurs had gone, so that changed what was happening to the forest floor. But at the other side of the coin is, and I mentioned the ash that came because of the impact a minute ago, but when that settled on the ground, because it all basically falls out of the atmosphere effectively, they're suggesting that it served as a fertilizer. So you end up with a much more nutrient-rich soil, and you get these fast-growing flowering plants, and they sort of bounce back in a way that some of the other plants don't. Actually, another quote from somebody called Bonnie Jacobs, who's at the Southern Methodist University in Texas. She says, "We love the way it ended up, this incredibly diverse, really structurally complex forest, but right now, we should be aware that we're living through a mass extinction caused by humans. Once again, ecosystems are being set on a different path. So there's a lesson in this, that comes back to us from the Cretaceous Tertiary boundary, that events like asteroids can change the whole ecosystem for another 66 million years. And we are kind of mucking around a bit too.
Yeah, what I found interesting was we draw a line where the dinosaurs stop and then life as we know it starts to begin, I guess. But the other interesting factor that came out of this is that you spoke of the conifers and the ferns that disappeared, but they were replaced by legume trees that produce pods and seeds, and they sort of don't exist prior to this impact. So it changed the planet to a point where you'd have to say it was an extremely dramatic change in the entire ecosystem and development of the planet's life cycles and the types of life that came about. And one wonders what humans might or might not be like had that thing never hit us.
Oh, yeah. We may well not have been here because...
maybe.
Dinosaurs ruled the earth at that time. They were big and ferocious, and mammals were small creatures that kind of cowered under the what cover they could find on the forest floor. We may be indirectly a product of that event.
And another thing that comes to my mind is I wonder if there was anything in that asteroid that ended up in the atmosphere after the impact that settled down and perhaps caused certain factors of life to change or alter. I don't know. It's a bit out there.
There is certainly one thing that was in it is what told us it was there at all, and that's the iridium that was present in the asteroid, which is not really found in any great quantity in the Earth's crust. But it is, it's essentially something that you do find in extraterrestrial objects. And it was basically Luis Alvarez and his son, whose name I can never remember. It's terrible. It's shocking.
Louis Jr.
Walter Alvarez. It's
close
to me. Yeah, Luis and Walter Alvarez. They were essentially geophysicists, but they discovered this layer of iridium that corresponds to the boundary where between strata that's got dinosaur fossils and strata that hasn't. And that was when they alerted two colleagues of mine in Edinburgh who were working on this at the time. I probably mentioned this before. Bill Napier and Victor Klube were working on the same thing, and they, basically the information was shared, although in fact Bill and Victor really didn't share in the glory of it all. It was the Alvarez duo that have shared in the glory, because they had a press release very quickly after that.
Yeah, well, fair enough.
Yeah.
He who hesitates is lost.
Well, that's right. And of course, we're terribly British in Edinburgh. We were
yes.
Scientists, actually, I should say, we were terribly British in Edinburgh because that's in Scotland. But yeah, yes. It was an unhappy time for Victor and Bill. I remember it very clearly because I was working with them, not on that topic, actually, on other stuff.
Fair enough. But yes, more information coming out of the study into the Chicxulub Crater, and who knows what else we'll discover. But the rainforests as we know them just didn't look anything like that or have the plant life that they have today. They were very, very different indeed. So what else are we going to learn, I wonder? We'll tell you when we find out.
Hopefully.
Yes. This is the Space Nuts podcast with Andrew Dunkley and Fred Watson.
Space Nuts.
This is episode 247 of the Space Nuts podcast, and Andrew Dunkley here with Fred Watson. And a big shout out to our patrons, the people who put a little bit of money every month into the kitty to feed Fred's cat and to, keep the website running, things like that. We thank you from the bottom of our hearts that you think we are worthy of a few dollars. If you would like to become a patron, just go to our website, spacenutspodcast.com, and click on the subscribe button. It's up on the top right-hand corner, whichever one that is, because I'm facing a camera and it could all be reversed. I have no idea. But you can click on there and see what options are available to you. You can subscribe to package deals, which gives you 2 or 3 podcasts, depending on what you want to do. Or you can just make a one-off donation, or you can become a patron through Patreon or through Supercast. What we're ultimately aiming to do is to make the podcast 100% reliant on listeners only. And that means getting as many patrons as we can. And it's good to see a few more have signed up in the last week or so, Fred. So fantastic. And thank you. Thank you so much. Let's move on to our next topic, Fred. And this headline has got me scratching my head. We're talking about intermediate black holes. Now, we've spoken about those before. There, up until recently, have been only 2 kinds found, little tiny ones, and others that are about, 55,000 times the mass of the sun or something, or maybe even bigger, some of them millions times bigger. Some of them as big as galaxies, as we talked about last week. But the ones that are middle-sized, the ones that are, somewhere around the 150 times the mass of the sun, are few and far between. And until recently, we didn't even know if they existed. Well, this headline, Fred, in Cosmos, reads, "Astronomers find Goldilocks black hole." Goldilocks black hole. What does that mean?
That's a really good question. It's not a headline I would have used. Goldilocks usually refers to things being not too cold and not too hot, but just right. But maybe it's a Goldilocks black hole because it has been, it's the sort of who has been sitting in my chair kind of side of Goldilocks.
Yeah, could be.
Maybe.
Could be.
But no, you're right that it is one of the puzzles of astronomy that we find what we call stellar mass black holes, which are up to about 100 times the mass of the sun, and the supermassive black holes, which start at something like 100,000 times the mass of the sun, probably usually bigger. Most of the ones we know about are millions of times the mass of the sun, and some are billions of times, like the one in M87 that was imaged by the Event Horizon Telescope. That's 6.5 billion times the mass of the sun. So there's this gap in the middle, the elusive intermediate mass black holes, as they're called. And there are a few suggestions of where these things might be found. There's some people have suggested they might be in the centres of what we call globular clusters. These are clusters of stars that we think are, well, they may be the remnants of the nuclei, the centres of some galaxies that our galaxy has gobbled up, smaller dwarf galaxies. But this field is still wide open. This story, though, relates to a probable detection of an intermediate mass black hole, and in fact its mass is right in the middle of that range. It's about 55,000 times the mass of the sun. That's the estimated mass. But it has been detected by gravitational lensing, which is a really neat trick that relativity allows us to do. When you've got a massive object in space, it distorts the space around it, and that can act as a lens, magnifying what you see beyond it. It's a way we study very, very distant clusters of galaxies. If a very distant cluster of galaxy has a nearer large cluster of galaxies in front of it, that nearer cluster will bend the space around it and act as a kind of natural telescope for the cluster beyond. It's a very, very powerful technique. But this story starts with something called a gamma ray burst. And we haven't talked much about those recently, but they're thought to be basically the emission of a pulse of gamma rays, very short-lived, not as short as fast radio bursts, but short, seconds sort of length of time. They are thought to be basically the result of stars colliding. Stars basically annihilate and you get these gamma rays. But they're short enough that if you had a gravitational lens, these pulses of gamma rays pass through it, you could find that you get two images of the gamma ray source because of the bending of the light. It's not a perfect lens. It can actually produce multiple images of the same object. And because it's a pulse that you're getting, you can look for the time delay between one arriving, one of the images arriving and another one, which has taken, whose light or whose gamma ray light has taken a different path through the gravitational lens. I'm not really explaining this very clearly.
I get this.
Yeah,
You're seeing the same thing twice at different intervals because of the disturbance to the space around travelling through.
Yeah, exactly that. And so what's happened is that by looking at the various quantities, and they are specifically how far apart the two images of this gamma ray pulse are, and what the time delay is in between them, the scientists who've done this work have been able to determine that they are seeing the effect of gravitational lensing around a black hole. But you can put the numbers into the into the formulae that relate to gravitational lensing to get out the mass of the black hole, and it turns out to be intermediate mass, 55,000 solar masses. And I might add as a footnote, Andrew, to this research, it comes from Australia. One of the authors is from Monash University, Eric Thrain, and Monash is a university in Melbourne that has actually a very, very strong school of theoretical astronomy in there. One of the theoreticians is somebody I know very well, John Latanzio, and they do calculations about the way stars work and about the way that stars evolved. This is, I suspect, from the same group, but we're talking now about gravitational lenses, which is a remarkable science. So this could be the first really concrete evidence of an intermediate mass black hole being discovered by gravitational lensing, one of the curious freaks of relativity. It's a very, very nice story. Yeah, and I'll shut up for a minute, but there is a postscript to it, which we might get to in a second.
No, I was just going to say it's interesting that they have perhaps discovered this through the observation of something else by the sound of it. So an event that headed our way on two different paths. So we received the information at two different times, and the byproduct is, oh, hang on a minute, the cause of that was an intermediate black hole.
Yes, that's right. It's exactly it. Yeah. So that's always very nice when something happens serendipitously and you get this a result that is something that you didn't expect.
No.
The postscript I mentioned is that one of the possibilities for the origin of intermediate black holes is that they may be primordial. That means they're remnants from the Big Bang. And the Big Bang remnants are not something that we've really got any proof of. It was suggested actually originally by Stephen Hawking many years ago that the Big Bang might have spawned many black holes ranging in size from tiny ones to what were they called? Slabs, I think, super large black holes. We talked about them.
That's right.
A few weeks ago. They were also thought to be primordial black holes. So an intermediate mass black hole, because it's too big to have been formed by a single star turning into a supernova, but it's too small to be found at the centre of a galaxy, may well have been formed in the Big Bang itself. So they might be primordial ones. And in fact, one of the other side effects of this study that we're talking about, the one from Monash, is that maybe there are very large numbers of these black holes in our neighbourhood of the Milky Way. And of course, some people have suggested that Planet 9 is actually a primordial black hole. It's not a planet at all. It's something much more interesting, orbiting around the sun.
Anything's possible. And I suppose it sort of brings us back to that thing whereby we suspect certain things exist, but we've never found evidence of them. But ultimately, we probably will. And just like we suspect that life might be quite prolific in the universe, at least at a microbial level. Intermediate black holes are probably quite prolific too. We just haven't been able to track them down as yet. That would be my theory.
Exactly. That's pretty well sums up the view of astronomers, that these things are probably out there, but we're not finding them in anything like the numbers we might expect. And maybe it's because they're the fact that this thing has no evidence of any other anything bright surrounding it. All they know is that the signal from the gamma ray burst arrived by two different pathways, but there's nothing to see. That in itself suggests that you're not seeing something that's gobbling up material from its surrounding galaxy. You're seeing something that's perhaps just lurking in space, which is what you would expect primordial black holes to do. So it does kind of make sense.
Just hanging around on a street corner, doing drug deals, just minding its own business and hoping it doesn't get caught.
But it's been caught.
Indeed, and will go to court and will be sentenced. Is fascinating, very interesting, and hopefully more to learn about the elusive intermediate black hole. This is Space Nuts, the podcast. Andrew Dunkley here with Fred Watson.
3, 2, 1.
Space Nuts.
Now, I wanted to say hi to everybody who gets together on Facebook, on the podcast group, and talks to each other. If you want to meet like-minded people that listen to Space Nuts, do a search for the Space Nuts podcast group and join fellow listeners, because they're a great community. They have a lot of fun, and they often have a lot of interesting discussions about this, that, and the other. I occasionally will pop in and say hello and maybe answer a question. Sometimes questions are directed towards us, and I make Fred's answers up because I just think that's a lot of fun. But yes, it's the Space Nuts podcast group. And you can find it on Facebook. Just put a search in for that. And while we're at it, also hello to our YouTube viewers who, for some reason or another, are increasing in number, even though they can see our faces. That is really lovely. So if you prefer the vodcast over the podcast, you can find us on YouTube as well. Now, Fred, something a little bit different this week. We're going to read some questions. We've finally transposed our massive text questions that came on a spreadsheet that basically was 3 kilometres long in one big string, and managed to whittle it down into manageable, edible parts. So let's get into our first question. Actually, it's a double bunger. Both our questions are double bungers this week. First one is from Andre in the Netherlands. Hello, Andre. He says, hello, Space Nuts. I have a few questions for your show which have been bothering me for a while. I'm sorry to hear that. First, our Milky Way has a diameter of about 150,000 light years. I would like to know how thick it is. Well, it is pretty dumb. I will say that. So how high is the cake is his question. Second, I would like to know if the plane of our own solar system is aligned with or tilted in comparison with the centre of our galaxy. And how is this for other solar systems in our galaxy? Are they all the same or different? Thank you, and keep up the good work. A fan of your show. Andre, thank you so much. Well, we might as well start with how thick the Milky Way is.
I think I'm
guessing he means top to bottom.
Well, in your thinking, he means in terms of its intellectual capacity, I guess, that it's pretty dumb.
I'm thinking he's
have you got
about the height.
Have you got any guesses, Andrew?
Well, if it's spread out 150,000 light years, I'm going to guess probably a quarter of that.
Yeah, that's an interesting guess. So we should make it clear that we're talking about the disk itself rather than the halo, because there is this halo which is nowhere near as dense as the disk. It's much more, the stars are much more sparsely spread out. It's where the globular clusters are that I mentioned a few minutes ago. And that's more or less spherical. So, it's probably 150,000 light years top to bottom. But when you come to the disk, the answer is a lot more interesting and just a little bit more complicated, because we define, and this actually comes from work that I wasn't directly involved, but friends of mine, people I work closely with, certainly were. It's got various components, and it depends which ones you're talking about. So, yes, 150,000, maybe even 200,000 light years in diameter. It's growing all the time, or at least our estimate of it is. The thinnest component of the disk is called the young thin disk. So there's two bits. There's the thin disk and the thick disk. But the young thin disk is where star formation itself is taking place now. And, the Milky Way's youngest stars are, as well as most of the gas and dust. It's the bit that we see when we look along the centre of the Milky Way. And the thickness of that is only about, up to about 500 light years, maybe less, maybe more like 300 light years. It's really very, very thin, almost like a blade through space when you think about it, given how big the diameter is. And then there is an older component, which is called the old thin disk. And that's stars that have basically migrated away from the young thin disk, so they're older stars. And that's roughly 1,000 light years thick.
Okay.
And then there is what we call the thick disk, which, and it was the difference between the thin disk and the thick disk discovered by scientists who I used to work with in Edinburgh, actually, years ago, it's more than 30 years ago. It's a long time ago. But the idea of the thin and thick disk is, as I said, it's been around for quite a long time. Neil Reed and Jerry Gilmore, I think, were the proponents of that, people I worked with in Edinburgh, still going strong in the world of astronomy. The thick disk is thicker, and it is round about something in the region of 5 to 10,000 light years. So, it's probably about 5,000 light years thick. Right. Compared with 1,000 for the old thin disk and something like 300 for the young thin disk. So the thick disk is very definitely a separate component. The work that I did with colleagues in the RAVE project, the radial velocity experiment that we did using the United Kingdom Schmidt telescope, we collected the speeds and physical parameters of 500,000 stars. And it was possible from the results of that to see the delineation between the thin disk and the thick disk, even though we actually tried to avoid the disk because there are too many stars in it. We were mostly looking at the halo of the galaxy with that experiment. Yeah. Anyway, a great question, and thank you for that. Moving on
sorry, I just need to clarify. Yeah. When we're talking thick disk and thin disk, are we talking layers?
Yes, in a sense we are. I mean, it's all done because you're talking about stars, which are individual objects, and not, something like gas. You're really talking about statistical things. But so the statistics are that there are a lot more stars in the thin disk than the thick disk, and you can imagine it as a layer between one and the other. It's probably not a very flat layer because, once again, there's probabilities involved. But really remarkable that we can now recognise these two characteristics of the disk. In fact, we recognise too that the halo itself is not uniform. There's certainly an inner halo and an outer halo, and they've got quite different rotational characteristics. So as we find out more about our galaxy, we realise its structure is more and more complicated.
Yeah, well, why am I surprised? Yeah. Now, he also wants to know about how the solar system is aligned or tilted in comparison with the galaxy, and is it the same for other solar systems?
The answer to that is no. The answer to the tilt of our own solar system is that the plane of the planets, what we call the ecliptic plane, is tilted to the plane of the galaxy. In other words, to the thin disk, it's tilted at an angle of 60 degrees. So it's sitting up at an unusual angle, nowhere near the same plane. And that is true of all solar systems. We find that they are at various different angles. I think people have looked for the kind of correlations that might say, 60 degrees is the most popular and there must be a reason for that. That's not been found. So yes, you have a quite a strong tilt of the solar system to the plane of the galaxy,
and that seems normal.
Yes, and that's normal, and it seems to be what you've got. You remember how the solar system was formed. You start off with a cloud of gas and dust that collapses under its own gravity, and it's the little random rotations within that cloud that eventually take on a preferred direction and a preferred plane of rotation. So the whole thing starts rotating. That could be in any direction, and that's why we get this randomness. There's a great question. Okay. Very, very nice to have Andre's question about it.
Indeed. Thank you for the question, Andre, and I hope we adequately covered your two elements today. Let's move on to a question now, a couple of questions from David in Springfield. He describes it as a dark matter quandary. Evidence for dark matter was found by observing that the stars of galaxies all move at the same speed regardless of whether they are near or far from the galactic centre. How then does a spiral galaxy even form with all stars moving at the same rate? Like water spiralling down a drain, the spiral shape requires the stuff towards the outer edge to be moving more slowly than the stuff near the centre, right? Dark matter should make formation of spiral galaxies impossible. Why aren't all galaxies of the non-spiral globular type if dark matter is real? And another question from David on the subject of terraforming Mars, which we touched on earlier. The red planet has a very thin atmosphere. Terraforming would have to invoke creating a practical atmosphere at a density more like it used to have a long time ago. With Mars having such low gravity, wouldn't any increase in its atmosphere we engineer just evaporate back into space like its original one did? If so, would the rate of that evaporation be at such a slow rate that we could maintain it, kind of like having a slow leak in a tyre? You just keep adding air once in a while. Yeah, I like that question. We'll get back to that. But yes, I got a feeling the answer to the first question is that spiral galaxies are a trick of the eye, which I think we talked about a few weeks ago. The spirals can only be seen under certain circumstances, and all galaxies aren't actually spiral galaxies. Is that what we said?
That's more or less it, yes, in the sense that the spirals are in some way an optical illusion. What David says is absolutely right, although I think the premise of what he's saying is wrong, because yes, he's correct in that the rotational speed of stars nearer the centre is more or less the same at the outer edge, but if the spiral was a physical property of stars, then you would still get the winding up effect, because the inner stars have got they have a much shorter distance to go around once than the outer stars, even though they're all rotating at the same speed. It's not rotating like a solid body. It's rotating with the linear velocity of all the stars being effectively the same speed, roughly 250 kilometers per second. And even in that circumstance, you would get a wind up of the spiral arms. And in fact, it would be wound up so tightly that's how we know that spiral arms are not just strings of stars. And as you alluded to, it's something else. And what we're seeing with the spiral is this wave of higher density moving through the disk of stars and gas. And as it moves through the gas, the pressure triggers star formation. You get all these high mass, short-lived stars which burn over only a few tens of millions of years, then blow up as supernovae, and you get this brilliance forming along the spiral arm. So the spiral arm is a wave, we call it a density wave, and that's why you've got these beautiful, gentle spirals rather than something really tightly wound in a galaxy, which is what you'd get if there really were strings of stars, because they're moving at the same linear speed, but they would the inner stars have got far less distance to go than the outer ones, so they immediately pull it into something looking like a clock spring, whatever a clock spring is. People don't know what clock springs are these days. I remember them well. Anyway, that's
young whippersnappers don't know what a clock spring is.
Right, yes, indeed. it's not the case that dark matter would make the formation of spiral galaxies impossible. In fact, it probably enhances it by. It may well be that the dark matter halo of galaxies stabilizes the density wave and gives it, that stunning property that we see in galaxies like M81, which is one of my favourites. It's got a beautiful spiral structure. Hope that answers the question.
Hopefully.
Moving along to terraforming Mars.
Mars. Now, you said earlier impossible, but he brings up a couple of interesting concepts which we should discuss. But let's say we did terraform Mars and we did create an atmosphere. It couldn't hold.
That's right. So what he's saying is exactly right. The density, the gravitational pull of Mars is insufficient to hang on to an Earth-like atmosphere. You lose the oxygen and the nitrogen very quickly. The evidence for that is sort of ongoing as well, because the last remnants of Mars's thick atmosphere are still disappearing into space. The Marvin spacecraft can detect oxygen, I think hydrogen, oxygen leaving the planet, being basically released from the planet now. So terraforming is a challenge. If you want to turn its atmosphere into an Earth-like atmosphere, you've got to do what David suggests at the end of his question there. Could we still maintain it because of the slow rate of evaporation? Well, I think the answer is maybe, but where are you going to get all this carbon dioxide from that you need to stabilise the atmosphere? And my guess, his lovely analogue of a slow leak in a tyre, which I like very much. You just got to keep pumping it up. I think you'd probably have to pump it up faster than, I think you'd struggle to pump it up faster than the leak. That's the bottom line.
Yeah, I think you're right. My theory is if we ever did go to Mars to put a permanent human presence there, you'd probably live in domed communities or something. You'd create an artificial environment and live in domes over the surface, and I think that'd be the only way to make it feasible, and even that would be a major engineering challenge. But who knows? One day that might just be the case.
Yeah. Well, my view on all this, that the ethical way to colonise space is to build megastructures. Like Halo Worlds, which has engineering that's probably not that much different from trying to terraform a planet. In fact, terraforming a planet would be much more of a challenge. Interesting stuff. But yes. I think you're right. I think domes on Mars are what we're going to see eventually when we get research stations there, perhaps. I hope we never try and colonise the planet, but if we get research stations, which I think is a good idea, we'll have humans living there, and they'd have to be radiation protected as well. That's the other problem with terraforming. How do you generate a magnetic field? Because you need that to protect the atmosphere as well as everything else.
We get lots of space wheelbarrows, and we just demolish Mercury or something and add it to Mars.
I've heard that sort of thing before. Oh dear, we tow Mercury out to Mars. What?
Or just ram them together and just wait a couple of billion years for it to settle down. Anyway, that'll work. Anyway, there you are, David. Hopefully we helped you out with your inquiry, and thanks for sending in your questions. And that brings us to the end. But don't forget, if you do have some questions for us, you can do that on our website. Just go to spacenutspodcast.com and you can click on the little tab that says AMA, which I'm doing right now as we speak. And it brings up the interface where you can either type a question in the old-fashioned way using our email interface. Whoever would have thought the day would come where I refer to typing an email as old-fashioned. But the other option is if you've got a device with a microphone, you just press the start recording button and it will record what you're saying. Don't forget to tell us who you are and where you're from and ask your question, and boom, all done. Simple as that. And while you're there, don't forget to visit the Space Nuts shop. There's all sorts of goodies there that you might like to add to your repertoire of useless junk at your place. But, you'll be helping us out at the same time. But, check it all out at spacenutspodcast.com. And, Fred, that brings us to the conclusion of another episode, 247 of the Space Nuts podcast. Thank you, sir, and it's been great fun, as always.
And thanks to all our listeners for sending in their questions, and we will get to more next week.
We will indeed.
See you later.
Fred. See you next time.
Bye.
Bye-bye.
Bye-bye.
Fred Watson, Astronomer-at-Large, part of the trio that creates this podcast. And hello back in the studio to Hugh. It's not actually a studio, it's a back shed, and he shares it with the dog. But that's okay. Plenty of dust there to put on Mars. But from me, thank you again for watching or listening and contributing, and we'll see you again next time. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.